Hi there, students. Before the beginning of every chapter, I like to tell you that at the end of this chapter, you will be an expert. So, chapter 4, periodic table of elements. Students, just watch this, focus, and trust me, you will be an expert at this chapter. I love this chapter. It's really fun. It's just a set of rules. Once you get it, you will be good to go. So, a periodic table. What is a periodic table? A periodic table has a list of elements, right? Hydrogen, lithium, sodium, calcium, all these elements arranged in a table. How are they arranged? We will get into that, okay? But it's important to know at the beginning that you have something called groups and periods. A group is a vertical column. So this is a group, this is a group, this is a group until here. We have 18 groups. Let's count them out, okay? Group 1, group 2, now group 3, group 4, group 5, group 6, 7, 8, 9, 10, 11, 12, group 13, 14, 15, 16, 17, and group 18. So we have 18 groups, okay, vertical columns. We also have horizontal rows, which are called periods, like this, okay. So we have 7 periods: period 1, period 2, period 3, period 4, period 5, period 6, and period 7. Okay, guys, quick note, don't care about lanthanides and actinides, okay, this is not going to be on SPM. So we already know that the periodic table has 18 groups and 7 periods, right? Now let's get into the very basics of a periodic table, guys. So how was the periodic table developed? There were many scientists who came about doing this. Let's just start with the first guy, Antoine Lavoisier. Now again, guys, you don't have to memorize all this and take, focus too much. This is just going to be a paper 1 question, maybe one paper 1 question. So just chill and enjoy this, okay? So Antoine Lavoisier. What did Antoine Lavoisier say? He basically said that, or what he did was he classified elements into groups, okay? He put elements into groups. What did we say groups were? Groups are the vertical columns. So, and he also classified elements into metals and non-metals. So he classified them into metals and non-metals, and he put elements in groups. That's all he did. Whatever he did obviously was not the best, too basic. It was a good start, but then it was further developed by this other guy. His name is Johann Dobereiner. Let's just call him Dobereiner, Dobereiner. Okay, what did Dobereiner do? He basically arranged 3 elements. Three elements with similar chemical properties. Similar chemical properties. Okay, guys, one more thing. Before we get into this, I just want to tell you the difference between physical and chemical properties. Physical properties is what we can see. So, the color of an element, how it smells, how does it feel. The chemical properties, it is what goes on within the element, the strength of the bonds, things like that, energy. We will get into those, but just understand that there's a difference between physical and chemical properties, okay? So, Mr. Dobereiner arranged 3 elements with similar chemical properties, and something interesting that he did was, so let's write down 3 elements, okay? X, Y, and Z. Now, these three elements were arranged such that the mass number or the nucleon number of the second element was the average of the nucleon number of the first and the third element. Does that make sense, guys? Let's look at an example, okay? So, Mr. Dobrynin gave an example of lithium, sodium, and potassium. So, students, what is the mass number or nucleon number of lithium? 7. For sodium, 23. For potassium, 39. So, basically what Dobrynin said was that the mass of the first and the third, meaning lithium and sodium, the total divided by 2, because he said the average, would be the atomic mass of the second element. So 39 plus 7, 46, 46 over 2, 23. Isn't that the mass number of sodium? Yes. So this is what Dobrynin said, and this law is called law of triads. So very quickly, we just think to ourselves, what did Dobrynin say? Okay, he arranged three elements in ascending order of atomic mass with similar chemical properties. The atomic mass of the second element is the average of the atomic mass of the first and third element. That's it, guys. That's all he basically said. And this law didn't really work. It didn't really work out well, because this only applied to certain elements, not all elements. You couldn't do this with every element. So failure, but then it started the revolution of the periodic table. So quite a good job by Dobrynin. Now move on to the next guy, and his name was Newlands, John Newlands. Same first name as me, so pretty cool guy. So John Newlands, okay, we just write his name down as Newland. What Newland basically did was he arranged 8 elements, okay, not 3 like Dobrynin, but 8 elements, again ascending order of atomic mass and what he basically said was that the first and the 8th element had similar properties, okay, and this law is called the law of octaves. So for example, I have let me see, hydrogen, lithium, beryllium, boron, carbon, nitrogen, oxygen, and fluorine. So 1, 2, 3, 4, 5, 6, 7, 8. 8. Sorry. What he basically said is that the first element and the 8th element have similar properties, okay. So just remember that, guys. This rule is called law of octaves. It's a good law, slightly better than the law of triads, but again it didn't work for all elements, okay. Now the fourth guy, Lothar Meyer. Lothar Meyer's work was really, in my opinion, not that big of a deal, but some people think that it's awesome. So all we have to do is understand, or just what I did was I just memorized this, guys, honestly. So what he did was he plotted a graph of, so just remember, Lothar Meyer plotted graph of atomic volume versus atomic mass. And what this means, guys, to be honest with you, even I have no idea. So what I'm going to tell you to do is just remember, if you see anything about plotting graph, atomic volume versus atomic mass, who did it? Just remember it was Lothar Meyer, okay? He also said that you saw some similar properties when you plotted the graph. You know, you saw similar properties for elements, but let's not get into this stuff. Basically, that's what Lothar Meyer did. Now, the next two guys are where it gets important. Mendeleev and the other guy is Moseley. So, we start with Mendeleev. What did Mendeleev do? Mendeleev, he arranged elements in a periodic table, but he did it based on atomic mass. So, he arranged elements in table in ascending order. Now, ascending means from small to big. Ascending order of atomic mass. Now, this was a very big breakthrough for chemistry. He did something good, and he was the one who said that elements with the same chemical properties were placed in a group. So, big development, but again, not the best development, because our modern day periodic table is based on not atomic mass but atomic number. So, let's just have a look at where he went wrong. The problem with what he did was, this was not, how should I explain it to you guys? It was lacking something, you know. There were some positions in the periodic table that he couldn't fill, and there were some problems with this, so it didn't really work out. It was an important breakthrough, but something was missing. So the next one to finish his work was Moseley. You see, guys, even I don't really, memorize this stuff. I just know the keywords. So the last guy, Mr. Moseley, what did he do? He basically said that elements arranged in ascending order in table, arranged in ascending order in a table based on proton number, which is how our current periodic table is today, right? It's arranged based on the proton number. So Moseley's periodic table is the one that we use today. If you look at our periodic table, for example, you see we have hydrogen, which has a proton number of 1. Helium has a proton number of 2. Lithium 3. So on and so forth. The periodic table increases in proton number as you move from left to right. So this is our modern periodic table. Let's just do a quick recap of the 5 guys. Lavoisier, Dauberreiner did the law of triads. Newlands did the law of octaves. Lothar Meyer, graph of atomic volume versus atomic mass. Mendeleev arranged elements according to atomic mass. And the last one, Moseley, arranged elements according to in increasing order of proton number, and he is the father of the modern day periodic table. That's all you need to know about these guys. Now we get into the heart and soul of periodic table. Okay, guys? So give me 1 second, guys. Okay, so now let's look at our periodic table. We have, as I mentioned, the elements increasing in terms of proton number as you go from left to right, and elements that are in the same column are in the same group. Okay, this is called a group. Now, how do we arrange electrons based on a group? The reason that they are in the same group, I won't explain it to you, I'll give you an example. Okay, let's look at lithium and sodium for a second. Lithium's proton number is 3, sodium's proton number is 11. Okay, so let's just write this down. Okay, bye bye Moseley. Okay, lithium and sodium. And we can also take, let's take potassium as well, okay? They are all in the same column, meaning all in the same group. Let's look at the proton number of lithium, 3, proton number of sodium, 11, proton number of potassium, 19, meaning that lithium has 3 electrons. What is the electronic configuration? 2.1. At this stage, we already know how to do electronic configuration, right guys? So I'm just going to move ahead. For sodium, it's 11, so 2.8.1. And the last one, potassium, 2.8.8.1. What is something common we see, guys? Look at the last shell. Do you see it? The same number of electrons in the last shell. And what is the last shell called? The valence shell. And the electrons in the last shell are called valence electrons. Okay, the word valence means last. So elements are basically arranged in a in a group based on having the same valence electrons. Okay, guys? Now, what are the names of the groups? Group 1 is called alkali metal. Group 2 is called alkali earth metal. Groups 3 up to 12 are called transition elements. This is very important, guys. We're going to talk about this transition element group at the end of this chapter. Group 17 is called, and we don't have any names for 13, 14, 15 and 16. Group 17 is called halogens and group 18 is called noble gases. Okay, guys? So, back to periodic table, we start talking about the periods. We have 7 periods, period 1, 2, 3, 4, 5, 6, 7. Periods go horizontally from left to right. How are elements placed in the same period? What is it based on? Let's have a look at it. So, let's compare elements sodium and chlorine, okay? And then we compare elements beryllium and carbon. So, sodium versus chlorine, beryllium versus carbon. Okay, what is the proton number of sodium? 11. What is the proton number of chlorine? 17. What is the electronic configuration of sodium? 2.8.1. Electronic configuration of chlorine? 2.8.7. Now, they don't have the same valence electron, right guys? But what do they have in common? How many shells are filled with electrons? 1 shell, 2 shells, 3 shells. How many shells are filled with electrons for chlorine? 1, 2, 3. You see it, guys? For elements to be in the same period, they must have the same number of shells filled with electrons. Both sodium and chlorine have 3 shells that are filled with electrons. So what period are they in? Period 1, period 2, period 3. You see the logic, guys? Now, look at beryllium versus carbon. Beryllium has a proton number of 4, so electronic configuration is 2.2. Carbon has a proton number of 6, so the electronic configuration is 2.4. How many shells are filled with electrons? 1 shell, 2 shells. How many shells are filled with electrons? 1 shell, 2 shells. So both beryllium and carbon have 2 shells filled with electrons. What period are they in? Period 2. See, period 1, period 2. You see the logic, guys. And for elements to be arranged in a group, their group is based on the number of valence electrons. Just now we said that sodium and chlorine both had, no, not sodium and chlorine, sorry. Lithium and sodium had 1 as their valence electron, right? So because they have 1 as a valence electron, their group is going to be number 1. Okay, let's look at fluorine and chlorine. Fluorine versus chlorine in terms of group, or we can do both group and period. So again, we need to look at proton number. For fluorine is 9, for chlorine is 7. So electronic configuration for fluorine is 2.7, for chlorine it's 2.8.7. So fluorine has 7 valence electrons and chlorine has 7 valence electrons. What group are fluorine and chlorine in? Are they in group 7? No, guys. It's very important to know that the groups, how they work are, you have group 1, you have group 2, and then you ignore this whole transition elements. For numbers 3 up to 8, for valence electrons, you have to plus 10. Okay, so what did we have here? We had 7 as the valence electrons for fluorine and chlorine. You have to plus 10 to this number. So 10 plus 7 is 17. Are they not in group 17? Yes, they are. So just remember this rule, guys. For groups 3, 4, 5, 6, 7 and 8, we always have to plus 10 with the valence electrons, okay? And now let's look at the period for fluorine and chlorine. Fluorine has 2 shells filled with electrons, so it should be in period 2, right? Chlorine has 3 shells filled with electrons, so it should be in period 3, right? Let's check it. Yes, fluorine is in period 2, chlorine is in period 3. So that's it, guys. You now know how to explain why an element is in a certain period and why it is in a certain group. Remember, it's important that when you talk about period, you always have to say shell, and this is a key word. You must mention this, filled with electrons. If you don't have the words filled with electrons, they like to cut some marks. So always like explain the word filled with electrons. So chlorine is in period 3 because it has 3 shells filled with electrons. So I've been talking a lot about this, guys. Let's go on with the material, see what happens. We know that group, as I mentioned in chapter 3 as well, group 1, group 2, all these transition elements in here, and group 13 are all non-metals, okay guys? Are all metals. All of these are metals. Group 14, we'll come to this later. Group 15, 16 and 17 are non-metals, okay? And group 18 is called noble gas. So we'll come to this later and I'll explain why it's called noble gas. Let's look at some example, guys. I want to just reinforce your understanding. So I'm going to give you a question, guys, and then we'll talk about it. Common paper 1, paper 2 questions, okay? So element R has a proton number of 16. In which group is element R located in the periodic table? So element R is just an example. It's not the actual symbol. So element R has a proton number of 16. When it has a proton number of 16, okay, let's just break this down. Protons are 16 and electrons are always the same as protons, right? So electrons are 16. So this is based on electronic configuration. How do we do the electronic configuration? 2.8.6, right guys? So group is going to be based on valence electrons. We have 6 valence electrons. Does it mean that group R is going to be in group 6? No, guys. Remember the rule for valence electrons of 3, 4, 5, 6, 7 and 8, you have to plus 10. Okay, so group R is going to be in group 6 plus 10, which is equal to group 16. What about the period? How many shells are filled with electrons? 1 shell, 2 shells, 3 shells. So element R is present in period 3. Now some of you may be wondering, what do I mean by shells? What I mean by shells, guys, are these electron orbitals. The first shell, you fill it with 2 electrons. The second shell, you fill it with 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. And the third shell, you fill it with 6 electrons. 1, 2, 3, 4, 5, 6. So if we count the number of shells, we have 1 shell, 2 shells, and 3 shells. Does that make sense, guys? Awesome. Let's keep going, okay? So, let's see. The book says the number of shells occupied with electrons determines the position of the period. We already knew that. So, let's do another question, okay? This is going to be a fun question. An atom of element T has 16 neutrons. Okay, I'm just going to write this down. T has 16 neutrons and a nucleon number of 31. So 31 is the nucleon number. In which group and period is element T located in the periodic table? So we know the neutrons are 16. We know the nucleon number is 31. When we talk about group and period, we are not interested in neutrons. We are interested in electrons. But we don't have the electrons, right, guys? Of course we do. Remember, nucleon number is number of protons plus number of protons plus number of neutrons. So nucleon number, which is 31, equals to number of protons, which is x, plus number of neutrons, which is 16. So to get the number of protons, 31 minus 16, number of protons equals to 15. And then we know, based on our chemistry knowledge, number of protons equals to the number of electrons, right? So we have 15 electrons. When we have 15 electrons, what is the electronic configuration? 2.8.5. So what group is this in? Group 5 plus 10, so group 15. What period is it in? Period 3, because it has 3 shells filled with electrons. You see, guys, it's so easy, right? They always ask this stuff on paper 2, you know, what group, why is it in a certain group, what is proton number, all these easy things that you guys are able to answer. Now, it's also important to know that elements in a same group, okay guys, I cannot stress how important this is. Elements in a same group will have similar chemical properties. What does this mean? Hydrogen, lithium, sodium, potassium, and these other guys over here all have the same chemical properties. And likewise with all these groups, fluorine, chlorine, bromine, iodine, astatine, UUS, which you don't need to know, they all have the same chemical properties. Okay, guys? All right, let's move on now. Excuse me. How are you guys feeling so far? Is it going okay? All right, guys, don't worry about this. We are like almost 25% done with this chapter. So we're going to talk about 3 groups right now, group 18, group 1, and group 17. Why these groups? Because these groups are special groups, okay guys? We start with group 18, and then on the next video, I'll talk about group 1 and then group 17. So group 18, okay? What does group 18 mean? It means that the last shell or the valence electrons should be 18 or 8. Obviously 8, right guys? Because remember the rule, whenever the last shell has 3, 4, 5, 6, 7 or 8, we have to plus 10. So the last shell in group 18 has 8 electrons. Let's take a look at group 18. So group 15, 16, 17. This is group 18. Okay, helium, neon, argon, krypton, xenon, and radon. You don't have to know about UUO, by the way, guys. So let's talk about some of the properties. Okay, I'm going to make a quick table for you guys based on the properties, and then we talk about it. So first thing we talk about is physical properties. What are physical properties? Physical properties are properties that we can see, things that we can, we can notice, things that we can smell, that can be perceived by the senses. So I'm going to write down the elements: helium, neon, argon, krypton, xenon, and radon, which I believe is Rn, right? Okay, good. Now, the first thing I'd like to talk about is we talk about the proton number. Proton number. Proton number for helium is 2, neon is 10. It basically will increase by 8. 18, but not always, guys. And the reason for that, don't worry about it, we'll come to that later. There are some rules in placing the number of electrons in a shell. So don't worry about that for now. We've put the proton number down. We need to understand the trend. Okay. So when we look at a group, always know that the proton number is going to increase as you go down the group. Okay, guys. When you go down the group from helium to radon, the proton number increases. Okay. Now, the next important thing, atomic radius. Now, these values, you don't have to memorize them, but these are just to show you a trend. I'll write them down for you guys: 0.05, 0.07, 0.094, 0.109, 0.130. Radon apparently doesn't have atomic radius. Now, let's understand this. When we go down a group, does the atomic radius increase or does it decrease? It increases, right, guys? And there's always going to be a reason for this. What is the reason for this? Let's look at the difference between neon and argon, okay? And this difference will be based on electronic configuration. Neon has a proton number of 10, so electronic configuration is 2.8. Argon is 18, that's its proton number, so 2.8.8. What difference? They both have the same valence electrons, but neon has 2 shells filled with electrons. Argon has 3 shells filled with electrons, and argon has a bigger atomic radius. So that's the reason, guys. The atomic radius increases as we go down the group, because as we go down the group, the number of shells filled with electrons increases. You see the logic, guys? Alright, guys, just give me a second. I'm going to connect my charger. Alright, guys, hi. Let's get back to this, okay? So we know proton number increases as we go down the group. We know atomic radius goes down the group because number of shells filled with electrons increase. Now, melting point and boiling point. I'll just put M and B PT, okay? Melting and boiling point. So remember what melting point was, guys? The temperature at which a solid becomes a liquid at constant pressure. And what was boiling point? The temperature at which a liquid becomes a gas at constant pressure. We studied this in chapter 2, remember, guys? Okay, so melting and boiling point for group 18, there are values here, so I'll just put the melting points down. Okay, minus 270 for helium, minus 248 for neon, minus 189 for argon, minus 156 for krypton, minus 112 for xenon, and minus 71 for radon. So what's basically going on? The value is, think you're going from a more negative value to a less negative value. Therefore, the temperature is increasing, right, guys? Because this is really cold, getting warmer, 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 and warmer. So temperature is increasing. Therefore, the melting and the boiling point increases as we go down the group. Okay, guys? And it's also important to know that group 18 is colorless. Okay, you can't see it. It's a gas, noble gas. You cannot see it. Has no color. And as I said, very low melting and boiling points. These values, I know you cannot determine if they're high or low, but believe me, these are very low melting and boiling points, and it increases as we go down the group. Now, what is the reason for group 18 elements to have a low melting and boiling point? Okay, guys, what I'm about to explain is something that you will see in the next chapter. You will see it in ionic and which is ionic and covalent bonds. You'll see it in carbon compounds. Anytime we talk about a low melting and boiling point, low M and B boiling point, the reason is the chemical bonds, okay, the bonds that hold the atoms. Now, for group 18 elements, they have bonds that are called van der Waals forces, okay. Just, I know this stuff sounds a little confusing, but just try to memorize it, okay. Van der Waals is a guy. Van der Waals forces meaning weak forces. So low melting and boiling point because of weak van der Waals forces. Now, let's think about this logically, students. When the bonds are weak, okay, let me give you an example. When the love between a man and a woman is weak, isn't it easier for the relationship to break? Correct, isn't it? But if the bond is strong, they love each other, no one can break the relationship. So same thing, guys. In this case, group 18 has weak van der Waals force. So the bonds are easily broken, meaning it has a low melting and boiling point. When the bonds are weak, guys, you only need a small amount of heat to break the bonds. Okay? And this small amount of heat corresponds to a low melting and boiling point. So I've mentioned a lot. I'll give you a quick summary. Group 18 elements have a low melting and boiling point. Why is this? This is because group 18 elements have a weak van der Waals force. So only a small amount of heat is required to break the bonds. That's it, guys. Okay. And does it increase as we go down the group? Yes, the melting and boiling point increases as we go down a group. Now, sometimes they like to ask why the melting and boiling point increases as we go down the group. So, what did we say when we go down the group? What significant change do we see? The valence electrons are always going to be the same. But what changes is the number of shells filled with electrons, right, guys? And when the number of shells filled with electrons increases, what was the first point? The atomic radius increases. So the link is, as I'll just write this down, shells increase corresponds to radius increasing. So, boiling and melting point increases as we go down the group because radius increases. Do you see the link, guys? Everything has to do, there's an interaction between each thing. So, when the atomic radius increases, you have more shells filled with electrons, and therefore you need more heat to overcome the force of attraction, even though it's weak van der Waals forces. So, I've stressed on a lot of this, guys. Let's move on, okay? We understand melting and boiling point. Now, one more thing that is important to know is density, okay? I've run out of space, so I'll create a new table. Helium, let's just look at three elements, guys. It's the same trend, okay? Helium, neon, argon. We talk about the density. Density is rho, the symbol. So density 0.17 for helium. For neon, 0.83. For argon, 1.66. So basically, we can tell as you go down the group, the density increases. Why does the density increase? Only one reason, guys. For this reason, when I studied chemistry, I didn't really understand it. I kind of memorized this reason. So I know memorizing is bad, but just do it this once, guys, and then you'll be good. So the reason why density increases as we go down a group, density increases, is because increase in atomic mass is bigger than increase in atomic volume. So, this is the key words, guys. Every time you see density, I think also for group 1 and group 17, if the density increases as you go down the group, why does that happen? Because increase in atomic mass is greater than increase in atomic volume. That's it, guys. In terms of solubility, solubility is the ability to dissolve. We won't get into that now, but noble gases are insoluble in water, meaning that when they are put in water, they don't mix with water, okay? So this is not a very important point, but I'll just write it down. Insoluble in water, all noble gases. Now, in terms of conducting heat and electricity, again, useless, okay? Cannot conduct electricity and poor conductors of heat. So, X to conducting electricity, elec stands for electricity, poor conduct heat. So basically, this is a very unreactive group, kind of useless. Now, we talk about the chemical properties, guys. This is where chemical properties come in place. Chemical properties have to do with reactivity, okay? So chemical prop of noble gas, prop meaning properties of noble gases. Now, it's very, very important to know, guys, whenever we talked about charges, remember, like sodium is Na plus because it's better to lose 1 electron than to gain 7 electrons. Chlorine is Cl minus because it's better to gain 1 electron than to lose 7 electrons. And remember when we talked about noble gases, helium, neon, argon, all of these, they never have a charge, guys. He, there is no He plus or He minus. There is no Ar plus or Ar minus. There is no Ne plus, Ne minus. Why is this? This obviously has to be a reason, right? So let's look at it logically. The plus and the minus, gaining or losing electrons is always based on electronic configuration. We always want the last shell to have how many electrons, guys? We want it to have 8 electrons to be stable, Now, let's take helium for example. This is actually one exception to the rule. Helium has a proton number of 2. What is the electronic configuration? Just 2. Now, we know that in the first shell, you must have 2 electrons. Helium has 2 electrons in the first shell. So, the first shell, which is its only shell, is full with the number of electrons, meaning helium is stable. It doesn't need to gain electrons, it doesn't need to lose electrons to be stable. So, it's stable. Let's look at another element in the group, neon. What is the proton number? 10. What is the electronic configuration? 2.8. Look at the last shell, the valence shell. What are the valence electrons? 8. It doesn't need to gain or lose electrons. It's perfect. It's stable. This sort of arrangement, when you have 8 electrons in the valence shell, is called octet, guys. Octet electron arrangement. Okay. The word octet stands for 8. Let's look at argon. Argon's proton number is 18, electronic configuration 2.8.8. Last shell has how many electrons? 8. Does it need to gain or lose electrons? No, it's already stable, it's already perfect. So it will not have a plus or minus sign. So anything which has a valence shell of 8 electrons is called octet electron arrangement. Anything that has 2 electrons in the last shell is called duplet. Now guys, this word duplet is only for helium and also for hydrogen and lithium, I guess, but only remember duplet, which means 2, and it affects helium. Okay guys, so I will read what the book says. Okay, reactive properties of noble gases. The outermost shell of helium atom has 2 electrons called the duplet electron arrangement. That's what we said, right? Duplet. Whereas the outermost shell, which is the valence shell of the other noble gases, have 8 electrons called octet electron arrangement. We already talked about this. The duplet electron arrangement for helium and the octet electron arrangement for the other noble gases are, what is the key word? Very stable. Does not need to gain or lose electrons. Hence, atoms of noble gases do not release electrons, they do not accept electrons, they do not share electrons. Therefore, all noble gases do not react with other elements or compounds. They don't need to react. They are fine by themselves. They want to be left alone. This means that noble gases are inert chemically or chemically unreactive and exist as monoatomic gases. I'm going to write these 3 words down, guys. So you have to remember these words, okay? Chemically unreactive. That means does not react with any other elements. It's always by itself. Inert chemically, the word inert means unreactive. It's another word for unreactive. And what is the meaning of the word monoatomic gas? Mono means one, guys. Remember when we were forming chemical equations in chapter 3, whenever you have a gas like hydrogen existing by itself, hydrogen was H2, right guys? Oxygen was O2, nitrogen was N2. Whenever you have 2 atoms, it's called a diatomic gas. So these are all diatomic gases. Now group 18 elements, noble gas elements, they are gases as well. But what are their formulas? Helium is He, neon is Ne, argon is Ar, and the same for the others, for krypton, xenon, radon. Why isn't it He2 or Ne2 or Ar2? Because they are monoatomic. They don't react with anything. Chemically unreactive, inert chemically. So they exist as monoatomic gases. Now, in an SPM question, if they give you a periodic table and they say, identify the monoatomic gas, just look at group 18. Only group 18 is monoatomic, guys. So, the last thing I'm going to talk about for this, for group 18, and I know you guys are getting tired, we're almost done with this chapter. If you ever get bored, just pause. I know I like to repeat myself, but I'm just giving you guys confidence because I know you guys are brilliant and you guys will get A in chemistry. So, uses of group 18 elements. Okay, very quickly, guys, we're going to go over this. Uses of group 18 elements. Now, you just have to know what I'm going to tell you. Don't bother about reading the book, okay? We just talk about each element. Helium. What is helium used for? Helium is used for making hot balloons, weather balloons, okay? You know those balloons that fly in the air? Weather balloons, airships. So let me just find a picture of this. These things, guys, these are airships, or they're also called weather balloons or hot air balloons, okay? This is what helium is used for. Helium fills these balloons. So anytime you see a picture of that, what element? Helium. Now, neon. Whenever I think of neon, I think of the city of Tokyo. What is so famous about Tokyo? It has lights everywhere. City that never sleeps. Everywhere you look, neon lights, neon lights. They're called neon lights, okay? So neon lights are present in advertisement boards. Why is it called advertisement boards? Because in Tokyo, you have many shops that advertise themselves, okay? So these advertisement boards are made from neon. Let's look at it. Neon advertisement boards. So images like these things, guys, you see? This is actually, I think this is Tokyo. So all these are made from neon, okay? Now, argon, AR, is used to make electric bulbs. What do I mean by electric bulbs? I just mean light bulbs, okay? Electric bulb, light bulb, same thing. So let's look at argon, electric bulb. It's the bulbs that we use in our houses, guys. Yeah, that one. Or these ones. These are all made from argon. Okay, guys? Now, krypton. They never really ask about krypton, but krypton is used to make lasers for eye surgery. You know the LASIK surgery? LASIK surgery for the eyes. Now, the laser is made from krypton. Okay? So anything to do with the eyes, krypton. The last one we're going to talk about is radon. What uses are for radon? We actually talked about this, I think, in oh no, we never talked about this. Radon is used to treat cancer. Okay, treat cancer, and it's radioactive. Radioactive meaning it's a little dangerous, but it's used to treat cancer. So a quick summary: radon is helium. What do we think of? Helium, we think of those hot air balloons, weather balloons, whatever you want to call them. Neon, think of Tokyo, advertisement lights. Argon, think of light bulbs. Krypton, think of lasers for eye surgery. And the last one is radon, think of treating cancer. If they say anything about radioactive, it's 100% going to be radon. Let me see, is there anything else that I need to cover for this chapter? 1 second, guys. No, that's it, guys. Awesome. we are done with group 18. We are done with the basics of group and period. Remember, anything from which has a valence electron of 3, 4, 5, 6, 7, and 8, to determine the number of group, which group it is in, you must plus 10. If the valence electron is 4, it's in group, not in group 4, but group 14. You got it, guys? Awesome. Remember about the 5 guys, Lavoisier and the rest of those guys. Remember about group 18 properties. For density, remember, increase in atomic mass is greater than increase in atomic volume. It is monoatomic, unreactive, inert chemically. And one more thing I wanted to talk about, melting and boiling point. Remember, melting and boiling point is low because of weak van der Waals forces. Think of a relationship between boys and girls. Weak van der Waals forces, you need a small amount of heat to break the bonds. And as you go down a group, the melting and boiling point increases because what was the link? Number of shells filled with electrons increases, so the atomic radius increases. So you need more heat to break the bonds. Okay, guys? Thank you. I know I've spoken a lot, but just bear with me, guys, okay? We're going to cover group 1 and group 17 transition elements, and you guys will be a master of periodic tables. Thank you, guys, and see you in the next video. Bye.